Hello, my name is Gonzalo Fernández and I would like to speak to you about the beauty in mathematics. More specifically, I would like to speak to you about the golden number, also known as the golden ratio. What is it? It is a ratio, a proportion, a relationship between two lengths which is sign of beauty, of perfection, of balance. It is also very often used in art because, as I said, this relationship is very visually attractive, is very balanced, it is a sign of perfection. It is also known as the golden number, the golden ratio, the divine proportion, and the golden proportion. What is it? It is the number 1.6180 and so on. It has an infinite number of decimal digits. And it is a proportion, as I said, a proportion between what? Two segments, A and B, in which phi, 1.61 and so on, equals A plus B divided by A and A divided by B. What does this mean? It means that if we divided the longest segment between the smaller one, we would get 1.61 and so on. Now, how do we get from this expression, from this equation, to the actual number, to 1.61 and so on? So we have that A plus B divided by A equals phi. And we, therefore, A divided by A plus B divided by A equals phi. A divided by A would be 1, and B divided by A is the opposite as A divided by B. And if A divided by B is phi, then B divided by A would be phi to the minus 1, the opposite of phi. This equals phi. And what do we do now? We multiply by phi both sides of the equation. We get phi plus 1 equals phi squared. Now we have that phi squared minus phi minus 1 equals 0. If we solve the equation, we would get that phi equals 1 plus the square root of 5 divided by 2, which is 1.6180 and so on. And now here we got a lot of interesting things, a lot of interesting mathematical properties that give this number an additional beauty, an additional mathematical beauty. For example, we got this here. 1 plus the opposite of phi equals phi. This means that 1 divided by phi, the opposite of phi, would be phi minus 1. What does this mean? It means that if we divide 1, if we divided it by phi, we would get phi minus 1. That means 0.6180. If we divided 1 to phi, we would get the same exact decimal digits, but with the 1 in front. This is one of some very interesting properties. Then we got this other one, which means that phi to the square, if we elevate phi to the square, we'll get phi plus 1, which is 2.6180 and so on. We also have that this here is also very interesting because phi equals 1 plus 1 divided by phi. To erase this. And this here is very interesting because this means that phi equals 1 plus 1 divided by phi. And what is phi? It is the same as this one. It is 1 plus 1 divided by phi. This is phi, so we can substitute it. And then we can continue. Phi equals 1 plus 1 divided by 1 plus 1 divided by phi, which is 1 plus 1 divided by phi. Then we could continue infinitely. We also had what I said before, phi squared equals phi plus 1. That is very interesting. And we also have that taking this equation, if we did phi equals the root square of 1 plus phi, then, as we did before, we could substitute phi and take the root square of 1 plus phi. And then we could do it infinitely the root square of 1 plus the root square of 1 plus phi, which is the root square of 1 plus phi. We can do that infinitely. Now I would like to speak to you about Leonardo da Pisa, also known as Fibonacci. This was a very interesting mathematician which in the year 1202 wrote the Liber Abaci. This was a very interesting book in which he made his biggest contribution to the European mathematics. Why? Because he exposed why the Arabical numbers were much better, much efficient than the Roman numbers that we used at the time. He also made the Fibonacci sequence, which is very known, and in which every number of the sequence is the result of adding the two previous ones. So we would start with 1, and then we would get 1 again because it's 1 plus nothing. Then we would get 2, we would get 3, adding the two previous numbers, we would get 5, 8, 13. And how is this related to the golden number? Well, it is very interesting. If we divide each number of the Fibonacci sequence between the previous one, we would get a number each time closer to the golden number, to the golden ratio. This one is more or less close and is lower than the golden number. This one is higher, and this one lower, this one higher, this one lower, this one higher. And each one is closer to the golden ratio. Now, I said that this golden number, this golden ratio, is often used in arts, is often used, yes, in common life, in common objects. But how? Well, most of the times through the golden rectangle. How do we get it? Well, we have a square with the side of A, and here is how we get B. We'll get the half of the square, and diagonal we dropped it down, and so this length would be B. If we drew the rectangle, we would have a golden rectangle. Why? Because its sides would be A plus B divided by A, which is in the golden ratio, A plus B divided by A. And this one here would also be in the golden ratio, because it would be one side A and the other one B. A divided by B is also the golden ratio, it's also 1.6180, and so on. Then where does this rectangle appear? In many common objects, in credit cards, in playing cards, in TV screens, in postcards, in art also, in the proportions of the paintings, and many other places. This number is also appears in nature, in the form of spiral galaxies, in the form of cactuses, in the number of petals of a flower. It is always a Fibonacci number, very related to the golden ratio. Also in the human body, if we divided the length of your forearm between the length of your hand, we would get the golden ratio. Also in the sequence of the DNA also appears the golden ratio. If we divided the length between the eyes, between the length of the white part of the eye, we would also get the golden ratio. If we divided the height of a human being, of a normal human being, average, between the length of the belly button to the toes, we would also get the golden number, 1.61, and so on. Also in art, why do artists use the golden ratio? Because it is visually attractive. It is a sign of perfection, proportion. It makes their paintings, when they use it, it makes them more beautiful. In many popular paintings or sculptures, it is used. In the Parthenon, it is a golden rectangle, if you notice. If we divided the length, the total length, between the height, we would get the golden ratio. In music also, Beethoven used it, Mozart used it, and also in many common logos, for example, because it is visually attractive, it is visually beautiful. And what is the point with this? The point is that in the same way that literature, that arts, that letters can express beauty, in the same way that they can transmit beauty, see beauty, and then the artist transmitted through letters, through paintings. In mathematics, we can also do that. Through mathematics, through mathematical expressions, we can also express the beauty that we see in the nature, that we see in human being. And in the same way that arts, that literature can create beauty through a painting, you can create beauty through a book, through a poem, you can create beauty. In that same way, you can create beauty using mathematics, using the golden ratio. Through mathematics, you can create beauty. That is shown because many painters, many artists use the golden ratio to create beauty, to give beauty to their poems or to their paintings, for example. And finally, it is in the same way as words have, in a poem, for example, words have beauty from itself, not only because they express beauty, but also because of the expressions that the artist uses, not only because what it says, but also because of the words themselves. In mathematics, the expressions, the mathematical expressions, the equations, as I showed you before, their properties give the number a beauty itself, and not only because of what it represents. Well, I hope you enjoyed it. Thank you for your attention.